All right. Here we are again for another week of Elm coding in the evening for fun and relaxation. I haven't really made up my mind what I am going to look at tonight, but I realized like there's a few things still going on wrongly here. We can move the tiles out of the screen and we can move the tiles into each other. So I think that's the next good thing to address. Cool, so I already fired up my... Oh no, actually did not fire up my build script, so let's do this right away. Compiling, firing up Vim. Cool, so yeah. I think the good entry point for me to look at is... So the errors happen when we press the keys. So when I press the key, something is not right here. So I think that's a good entry point to start our investigation from. I guess left, what is left arrow? What do we do when we have left arrow? Let's search new tiles. Which function is this? Move piece. Yeah, move piece sounds exactly like the thing we should fix, or I should fix. So let's see how this gets called. Okay, so if we press a key down, move piece, that's fine. I think I would like to keep this, the call from this, as simple as possible here in our update function, because naturally I would say that's the update function is a place that keeps growing over time, because eventually all our messages are going to be, at least from our top level message type, will have to be caught in this big one case. So we want to make our calls as concise as possible. So let's jump back to the definition of move piece. So yeah, if we don't have a current piece, we do nothing, so that probably stays the way. And now, like, this is also a bit grown. It's a lot longer than one screen page, so maybe that's also an opportunity to simplify a few things here. New position, new tiles. So basically, we introduced the new tiles last time, because if we rotate, then we change the tiles of the current piece, the little elements. Whereas when we move, then we actually only change the position of the current piece. So this is maybe already something worth breaking out. Move piece, new tiles. Yeah, so, but before we do this, actually, I think I'd like to add the new logic that keeps us from moving the current piece into a position where it cannot be placed before we clean this up. And the logic, the algorithm I would use for this is basically I will try to find out which tiles the current piece would occupy after we place it in the board, or when we try to place it in the board, and if any of those are not empty, then we basically must not make the move. So current piece, move piece. So basically that should be rather straightforward, I think, because I think we already have a function. Or maybe I stepped into this trap again already, I fear, a few episodes ago. To look up the translated tiles, or whatever. I think something like translated tiles. Translate to current pos. Translate to current pos. Okay, I grabbed this again. I know that's how the mistake started in the gravity episode than the first one. So I will make sure I pay a bit more attention to days. So what we want to do is, like, we want to translate the tiles in the current piece to the position of the current piece, or of the moved piece, as I called it here. So tiles. So this would be, whoops, moved piece. Or maybe we write a top level function for this. Actually, let's do this, because I feel like we don't want to unnecessarily blow this up. So let's say occupied fields, because that was really what the elements of the board are called. And we take a current piece and a board, and we, or maybe we just start with the positions. So list position, occupied, then it's also more like occupied positions. Okay. And we can deconstruct into the things we're actually interested in right away. So this will be the position and the tiles. I feel I want to have a few local expressions. That's why I start away with a let block. Positions will be our result. And I know we have to do something for every tile, so I know definitely I will have a map, and I will map over the tiles, and we have a function that I just call f, or maybe let's call it, because I know already what I want to do, right? I want to translate each tile relative to the current position of the current piece. So let's call it just translate. And we also know from the way I want to call translate with the map that the parameter to this will be a tile, and I don't know how tile is defined. Let's look at the type declaration of current piece. Type alias current piece. Tiles are just a list of position. One position is wonderful. So I know one position has a X and a Y. And to translate it to the current position, maybe I make X and Y the elements of the current position, and we will call this TX, tile X and tile Y. So we just add those together, TY plus Y. So that looks good. And I think actually we can just do this, and that's why. This way we have a nice little helper function. Compiles without errors. Wonderful. So let's say occupied positions. Well, I must not call it the same way. Well, let's call it first and then come up with an identifier for the local expression. This will be move piece. Okay, let's call them moved positions. And for each position we want to look up on the old board what field is in this position, and we want to find if any of those are not empty. So I think we have a lookup function to, or maybe to find our lookup. But it's not a top level function. No, we don't have a top level function that lets us look something up from a board. Okay. But we can easily make this a top level function. So let's just see if I used any local expressions that makes the compiler unhappy. No, it works right away. So that's nice. Let's give the top level function. That's a good habit to give at least the top level function signatures right away. We are taking a position and a board, and I guess we return a maybe field. Maybe field. Let's see if I guessed this right. Yes. Awesome. So now we have all the positions that our current piece would take if we would allow to move it. Now we have to look up the actual fields for those positions on the old board. So we'll do another map. We'll do a lookup. But the thing is, that's a typical functional programming problem. That let's write what I wanted to do. Look up moved positions. So that's fields under moved piece. Let's be very verbose here. So this will not work because look up takes a position and a board, and we only give it positions. So now but like for all of the lookups we do, the board will be the same. But the problem is I cannot use partial function application here because the parameters are in the wrong order. And I think there's a function for this, flip, but that will turn around the arguments on the form. Really magical. But I had never used it myself, I have to admit. So let's make it first explicit, and then maybe we can do a little refactoring. So we'll do a little local function, look up flipped, takes a board and a position and calls look up with position and board. So now we can call look up flipped. And it doesn't work because the second argument is move positions. Because I didn't actually bind the board to it. So I guess this would be model.board. And now it's compiling in. So this is nice. And maybe do I look up flip now? Okay. So like I'm a bit on the fence because I on the other hand think maybe we should solve our problem first. Yeah, let's do this. Like I will come back to actually optimizing, like trying to get rid of this ugly intermediate flipped helper function a bit later. Let's try to solve our problem first. So now we have looked up all the fields on the old board that are under the tiles after we moved the piece. So I would say can move. So can move is if all of the fields under the moved piece are empty pieces. Only then we're allowed to actually put our piece or move our piece where we want to move it. So we can just use the all function. Did I import this already? No, so I have something in my head that I want to use. Elm list. Yeah, that's not what I was looking for, but close enough. List, and there is a function called all. Determine if all set elements satisfy some tests. So all elements should be equal just empty. So let's create a little lambda function here. F, and this is F equals just empty. And we map over fields under moved piece. So now we can actually say if can move. Then we do what we did before. Whoops, not that. Else we do nothing. We just return model, I guess. All is, yeah, I forgot to import it. So I'll quickly jump to the top to the imports, look for my list import and add all to the function, to the list of exposed functions from that module. Compiled without errors. Oh my god, I'm so curious if that fixed it. So let's refresh. Boom! I'm pressing vividly the arrow button. Oh, I can move it to the left, so that didn't solve it. But I cannot move it to the right, so that's a partial success, I would say. So let's see if we can move, if I can move tiles into each other. Ah, does also not working, is also preventing that from happening. So that's another success right there. And can I, oh yes, awesome. That's fine. Cool. So now the only thing to find out is why we can still move it when it's beyond the left edge of the board. Let's increase the font size here a bit. I'll just sprinkle some debugging juice over this, I think. So let's debug the fields under the moved piece. I'm using the trick that Martin told me the other day on Twitter here again, where I just replace one of the expression that I want to debug with the debug statement itself. So now we can reload, and we see each time we hit the key, it's logging something out, so that's good. And now I have to be a bit faster. Clear. Boom. Oh. So now we see, okay, they are all just empty, although we're in the negative x coordinate, so this should not work. And that basically means that our lookup function is somewhat broken. So I'll fix that first. Oh yeah, and I must not forget to look up the flip thingy. Okay, nothing. Or maybe we actually, I have my little test suite, so I think I'm going to fix this in a test-driven way. Bump up the font size here a bit, and I believe the command is elm test -- watch. Running in watch mode. Our tests are passing. Wonderful. Let's open up this wonderful test file. Could also maybe use a new name rather than example elm, but not super important right now. So I'll just copy one test here. Test. Change in quotes. Look up returns nothing for look up outside of board. So I think I'm going to steal a bit of this here. Current piece we don't need. Make empty board 3 3, okay, and then we say, well, how do we write our expectations here? Expect equal nothing. And what do we want to test? We want to test look up minus 1 1. Cool, let's see. Oops, nothing. Nothing. What? This nothing value is a maybe A, but equal needs the second argument to be... Ah yeah, I didn't pass in the board. That makes sense. Empty board. Ah yeah, and there we go. That's where the magic is not happening. So let's go about it and fix it. So now we can actually say we only want to execute this one test by prefixing the test call with the only function. Running one test, wonderful. So let's go into the definition of this. Case MB row. What does MB row? List head. So this we definitely have a row because our yeah, okay. Basically, yeah, we are not dropping anything from our columns. So we find our row because our y coordinate is fine. And like maybe we write 2 tests actually. One for left outside and one for below look up below of board. That's good. I will just drop the only to see that we have now 2 failing tests. Oops, and something is off here with the... I forgot the comma for the test array. And now we have 2 failing tests, one for the left outside and one for below of board. So now I will pop back in the only to only work on one test. So the reason we are finding empty is because for the test with that looks on the left is we have the coordinate x is -1, y is 1. So let's go step by step through this function. We're looking at maybe row. Maybe row drops the 1 ty rows from all rows. So it drops 1 row. It takes the first element from that list. So we're in the first row. So that's all good. That means we are here in the just row fields case. And then from these fields or columns in this row, we are dropping tx fields. So we're dropping a negative number. So I think that means in Elm it defaults to not dropping anything. So that means we take the full row and take the first field, and that is empty. So that's why we get it just empty here. And I think the easiest way to get out of this is like be really explicit about this and be like, if tx smaller smaller than 0, or ty smaller than 0, then return then nothing, and only that's not the case, start our dropping algorithm to find out the actual field. So cool. Now it tells it's not green but yellow because we are only running one test. So let's remove this one. Now our test's passed. So that means we can fire up our application again. And pressing left, and it doesn't go outside of the screen. So that's lovely. Neither to the right nor to the left. Awesome. Cool. I'm going to remove this debug statement here. So we are going to delete to the second quote. And this parenthesis is also too much. So this should still do the thing. Yes. Now the logging is gone as well. So now I want to learn how flip works. As I said, I've never introduced this function myself. I probably have copied some code that uses it from somewhere. But, and I think the signature is nice, abstract, something to puzzle about. So let's see. Flip. It doesn't exist. So maybe it's not part of core. Let's see. Elm flip arguments. Boom, flip argument. Oh, maybe it. I know definitely it exists in Haskell, which is the language that Elm took a lot of inspirations from. But maybe it doesn't exist actually in Elm. I'm trying to modify. Flip was removed from Elm core in 19. Ah, there we go. Yeah, that's exactly what I tried, but it didn't show. So let's see. Maybe we can actually write it ourselves. That would be even more interesting. Oh yeah, let's do this. That's nice. That sounds exactly like one of the exercises our professor would make us do in the functional programming lecture. The old flip from one, it only takes two, and then in reverse order. Good for pipes. Okay, cool. Flip. Yeah, that's what I want to do. Okay, so what I want to do is, instead of having to explicitly write out this call, I want to be able to write flip lookup. And I don't want to be specific about the arguments either. So this will obviously not compile because I didn't implement the flip function. So let's, oh, this is, maybe it's much less spectacular than I think it is, but it's after all a fun exercise. So we want to write a function called flip that takes a function that takes one parameter and a second parameter of unknown types A and B. That's why these lowercase variables are type variables that indicate a type that we don't know about at the time of writing, and I'm not even sure what this function returns. And it, like the function I'm passing in, I do know what my flip function should return. It should return a new function that takes an B and an A and still returns a C. Cool. Flip, let's call it F. Maybe it is as spectacular or tricky as I thought it would be. Because like we still want to call F, right? So I basically have to take away the parentheses here, because now I can actually write out these other two parameters explicitly, A and B. And now these A and B are not type variables anymore. Now they are names for actual parameters of our function call. So now, and then I don't need this. Okay, that's a nice brainfuck. I'm curious, does this work? It works! It works! So we just implemented the flip function ourselves. I think it's not worth to have a dependency on a library for that one function. I think it's also fine to just implement it ourselves. So yeah, now we created this flipped function in this much more elegant way and reusable way. So now we can actually maybe replace it here and inline this expression directly, because it's so short now. And we might have to... No, it works. All the operator precedence is right for us. That's so nice. It just works. Cool, 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 cool. All right. What time is it? Half past. So we spent a good half hour on this. I think I might write up a bit about this, what we did here. I'm not sure if it's entirely clear. That's really the beauty of functional programming. There's like somebody more functional programming literate than I can probably tell exactly what we're doing here. It has something to do with currying and uncurrying. But yeah, I will make it my homework to look this up and write it up in the summary for this episode. And maybe we can, as I said in the beginning, our method here, our move piece method, is really long. So maybe we can just break this up into something a bit more, a bit shorter. I'm just not... yeah, so maybe actually we can join those two case statements. That's something... And that's also something nice to show. And like in terms of language features, we can actually construct a tuple here right away by assigning it to like this. And then instead of having a branch for each, we can just construct the tuple here right away. So and now I'm just making space for our branches to receive the values for the rotation case. So here, because it's actually, yeah, I think that makes sense. I mean, this is not what I did with the comma here, but if we clean this up a bit. So in the case of left and right arrows, our tiles remain unmodified. We just change the position of the current piece. And same thing for the... Like we can actually write it out, or do we? No, yeah. Here we can just say current piece dot position, and the real magic for the rotation happens in this expression. So let's just move this over here. Map rotate tiles. And I mean, one could even argue it's not worth having a local let block for this. So let's turn this into a lambda expression here. Boom, throw this in here. I mean, we can still be nice about it and just break it up into 3 lines, and then we still keep it readable. Then we can remove this entire block here. Boom, is the compiler happy? Compiler's happy. We can still rotate and move the piece around, so then I am happy as well. What else do we do here? Tiles, what do we do with the tiles? That's not even necessary, this local assignment. Like, I think it's more explicit if we actually say those are the tiles of the current piece. Then we can remove another line here. Good. Move piece. And we can sprinkle some function composition maybe over this as well. So let's see, what are we doing in those 3 expressions? Moved, like we can inline this for sure. So, I mean, that doesn't necessarily make it more readable. Or maybe I just copy it first and then I can see if I like it, and it's easier to revert eventually. So now I can throw this in here, but I have to put in this. I don't know actually what's the name of this operator, but it's basically, it's either this or placing parentheses around the expression. And this like makes it just more streamlined to write it this way. And now we can copy this expression and inline it here. And we do the same thing. Well, actually, I like this better already. It compiles, and when it compiles, it's also always a high likelihood of it still working the same way. So yeah, we can do some, like, it's really the cosmetics and this particular taste of functional programming. And I don't consider myself a professional functional programmer, but I do start recognizing that I pick some of the patterns up that I in the beginning had a hard time grasping. For example, we can simplify this lambda expression here. Instead of saying, oh, we get an f and this f has to equal just this value, we can simplify all of this to, because the equals operator is also just a function in the end. So we just, and the equals operator is a function that expects 2 arguments and returns the Boolean value if they are equal. So if we pass in only one argument, the just empty here, like if we, then again we are partially binding this argument to the equals function that previously expected 2 parameters, and now it's only expecting 1 parameter. And I've been very generous with parentheses here because also I know the Elm code formatter is very opinionated and good at just removing parentheses that are not needed, but apparently they are all needed. So now one could argue, like, is this prettier or better readable? But ultimately at some point it just comes down to taste, I would say. So we can do it. Well, no, I think I'll leave it at this. So if can move, then like our logic is still as before. Let's see. Yeah, I think that's better. Cool. So I think I don't start. Well, I won't start a new topic today. Keep it a bit shorter. I don't know what to look for next week. I think, like, or maybe like one small thing I can sprinkle in is to add a few piece definitions so that we not only have the T and I think the J piece, but a few more pieces, because then we're all set up to look into actually clearing rows next week. I think that's a nice next task to look at, because currently, I mean, I guess the pieces are enough to produce some full rows. Oh no, that wouldn't be one, but like just as a farewell into the next week, maybe little reward by adding one of the or two of the other pieces. So let's add the L piece, which is symmetrical or mirrored J piece, basically L piece. And now I have to find out this is the center. We have one to the left, one to the right, and one. Okay, so I guess I have to invert this one. And let's make it green. Oh no, let's make it purple. Purple, because I think I want the Z to be green, or S piece to be green. So where are we keeping all the piece definition? Here, L piece. And now we're reloading, and it's not compiling because I didn't define purple. So where do we define blue? Oh, I can already tell. I will need to add a branch here as well. Purple. And I think there's a web purple. There's an actual color, web color named this way, so no need to bring out the hex code. Purple. Compiler's happy again. Reload here. And now we just have to wait until the random generator is generated. Ah, there it is right away. The L piece in purple. Isn't that beautiful? And L, yeah, it's an actual L. Because there's a J. Awesome. Loving it. And now to the Z piece. Copy the T piece definition. So I can just go to my inspiration, Sean. By now his URL is in my address bar lookups. Where are the T piece definitions? Did I go over them already? Ah yeah, here. Z. But I think his coordinate system is set up differently. Okay, so the centerpiece is clear, and then we have one that is to the left and to the and up, so that's right. Then we have one that is at the same, at the same x coordinate, but one above. And then we have one that is to the right and on the same level. And this I want to be green. So let's look up where we added purple. Here. Whoops, that was wrong. Let's add another case for green. Green. Copy here, align in the color definitions, add another line for green, save it. It does compile. I didn't change the I didn't change the name for it, so that would be, what did I say, the Z piece. And I also forgot to add it to the list of piece definitions, so let's put it here, Z piece. Compiler is not happy. Why not? Line 80. I saw a type in these. Where's these? Ah, here. Z piece. Now the compiler is happy again. Let's spawn a few tiles. Keep the fingers crossed. With every new tile, the likelihood of actually seeing the new tile reduces. Here's the nice piece, delicious. It starts getting actually playable. And there is our next candidate, the Z piece. Oh yeah. Okay. Cool. Loving it. Yes, so that's the challenge for next week, to tackle, to have those full lines actually being removed. All right, thanks for staying with me. Looking forward to next week. Ta-da.
Know how to take those in your head and in your heart and say something meaningful.